can pull out the slides. Okay, listen. We have to live with this. And if you have your computer, you can pull out the slides from Moodle so that you don't have to stare at this. Huh?
You tried just moving it from the computer?
This is what's doing it. Not this.
You tried it though?
I didn't. Could it? It has to do with it?
Maybe. Yeah, it was your computer.
Mycin doesn't need the +2. Okay, let's continue where we left off. Bring up your sheet of paper that you were supposed to solve this and turn it in for extra credit. So, do you agree or disagree with your boss? Is it politically correct to disagree with your boss? Okay, come on, tell me.
I agree that it takes overnight to do it.
You agree that you want to switch to wet?
Yes.
Okay, what about Lucy? What do you have to say?
What is this wet ashing only for like preparation stuff and non-content, so you can't even get to the lab?
Listen, guys. Go ahead and repeat what you said.
Is it wet ashing only used for like preparation stuff for mineral content, so you can't get to the ash?
Yes. I would disagree with your boss because wet ashing is not going to give you percent ash. It will only, like Lucy said, it's a preparatory step when you are only after determining certain minerals. If you really want to get percent ash, wet ashing will not work. So you will be explaining this to your boss in a very politically correct way and tell them, no, you're wrong. Not considering the time issues. Okay, yeah, that's it. Not considering the time issues, you would want to continue to get percent dry ash. What might you change, or why? Can't read. Why might you change to wet ashing? And we said that only if you are after a certain mineral content rather than total ash. Okay. That's it. Turn in your sheet of paper with the calculations from last time to get the extra credit. And you can do that at the end of lecture. They can do that at the end of lecture. All right. Why are you chatty on Fridays specifically? Okay. All right. Which of the following is true? Okay. A. Were you going to say A?
I was going to say
Brad was going to say A. Okay, so it is A. Oil has lower melting point than fat. That's why fat is solid at room temperature. Oil is not. And fat has obviously more saturated fatty acid compared to the oil. And saturated fatty acid will have higher melting points. Okay. The lipid portion of the food Emma or Stephanie said C? Just C?
I think it's C for sure.
C for sure.
I think it's E.
I think it's B and C.
I think it's A because those are fat soluble vitamins.
So just A.
Oh.
Well, I think the answer includes A.
Yeah, the answer includes all of it. So vitamin A and D, or A, D, E, and K, EDIC, are all fat soluble, so they will be extracted with your fat. And also the fat or the lipid has varying polarity. You have the phospholipids that are polar lipids, for example. Triglycerides are non-polar lipids. So you have a different range of polarity of your lipid fat. And because of the different range in polarity and composition, ethyl ether alone will not be able to extract all of your fat lipid components. Okay. So what's the definition of lipid? I don't know if you go over that in food chemistry, but what's the definition of lipid? It's a very simple definition. Okay, Katie? Huh? You're close. It is the component of food that would be extracted by nonpolar solvent. That's how it's divided. Anything that is not soluble in water and extracted with organic solvent. Okay, so simple lipids, they can be esters of fat, such as triglycerides, di and monoglycerides, emulsifiers. Di will have only 2 fatty acids. They will be more polar than triglycerides. And monoglyceride will have 1 fatty acid, also more polar than your triglyceride. Other esters of fat, vitamin A is an ester with fatty acid. Instead of having glycerol, it has retinol as your alcohol. You have compound lipids. Phospholipid is a compound lipid, so you have your glycerol, and then you have the 2 fatty acids, and then you have a phosphate group. That's what makes it more polar. You have lipoprotein, glycolipid, cerebrosides. All of these are different types of lipid that contain not only lipid or not only lipid, but have other components, proteins or sugars. Derived lipids, these are not necessarily your ideal or the typical lipid. 3 fatty acids, they would come from hydrolytic rancidity. And then long chain alcohols is also, they are the result of hydrolytic rancidity. When you break the 3 fatty acids, you'll wind up with alcohols. Hydrocarbons, so if you break off the chain, remove the carboxyl groups from the fatty acid, then you will end up with a large chain of hydrocarbons, or long chain of hydrocarbons. Fat-soluble vitamins are derived lipids as well. Okay, that's it for your food chemistry review. Why is it important to analyze fat content? Why do we care? We always have to ask ourselves this question. Ethan.
Because it's one of the major sources of energy for us, and over-consumed fat could lead to health problems.
Okay, so fat content for health problems has high. Okay, that means food scientists, we care to report this on the nutrition label. Makia? For spoilage, yes. If you have high fat content, you will have shorter shelf life. So you really need to know how much fat you have, how do you control lipid oxidation or lipid hydrolysis. Yes, Billy.
Fall within the standard of identity?
Standard of identity, of course, because a lot of different food products, especially cheeses, for example, you would have a limit of how much milk fat you can have, or lowest and highest. So what else? Emma?
Meats manufacturing.
Yes, meat manufacturer specifications. That's true. Okay, so nutrition label, regulatory requirement, manufacturing specification, stability of your lipid component, because they would have shorter shelf life due to rancidity. Okay, So analytical methods, there are a number of analytical methods. Some are based on solvent extractions, quite a few. So we have the continuous solvent extraction method, that's the Goldfish, and I'll talk about that. Semi-continuous, which you did in the lab, that's the Slit. Discontinuous is vagina, you also did in the lab. And then a couple more that are considered elevated pressure temperature, that is super critical fluid extraction, SFE, and accelerated solvent extraction. So we'll talk about this. And the GC method, so you would extract the fat and then you would convert the fat or do saponification and do esterification to get free, and then analyze all of your fatty acid to back calculate your lipid content. Non-solvent extraction or wet extraction, we're going to have two. We have two that we'll talk about today. And then instrument methods, NIR or mid-IR, NMR, and Falsley method. And we'll talk briefly about them. So before we start, we have, of course, to do sample preparation and think about the solvent. There are so many different solvents that can be used. So in order to determine how we're going to prepare our samples, we have to think about the type of food that we have. Okay, so is it high in moisture? What we need to do? Is it high in carbohydrate? What would best to do if we have high protein and fat but low carbohydrate? What would be the best way to prepare the sample? So we'll talk about this in detail. We've gone through that in lab as well. So type of food is important. Nature of lipids. Do I have high amount of polar lipids or do I have mostly triglycerides, non-polar lipids? So that would determine what type of solvent would work best in this case. Extraction method. What would I select if I have Soxit and Modiner? Which one would I go with? Which one will give me more accurate results? Okay. Isn't it obvious? Go ahead, Mallory.
The above?
Yeah, we've done all of this in the lab, right? Some of the samples we had to pre-dry because they were high in moisture and we wanted to do Soxlit. And Soxlit specifically requires that the moisture content not be less than 10%. So we had to pre-dry cheeses to run Soxlit. We had to do acid hydrolysis for the Modiner step when we were working with high carbohydrate. Here's why, and here's an example. When you do acid hydrolysis versus no acid hydrolysis, you have enhanced recovery of fat. So the acid hydrolysis allow the fat to be released from a complex matrix. So if you have high carbohydrate and protein and very low amount of fat, it's very hard to extract because the fat will be entrapped. So it's better to hydrolyze so that you can obtain better results. So if you take flour, some of you did whole wheat flour, it really has very low % fat. You'll see when you calculate the data, if everything goes at theory implies, and oftentimes we don't get theory implied with our work, but if all goes well, you'll see that Modiner will have more accurate results for high carbohydrate than Soxit. So here, Soxit, if you have low fat content and really high carbohydrate and protein, Soxit is not the ideal way to go. So you've done Modiner as well. With Modiner, you do some sample preparation to release the fat. So when you have very low amount of fat, you will be able to get better results using Modiner. Soxit usually is used mostly for high-fat food, meat products, cheeses, nuts. That would be excellent method to use Soxit. You can use Soxit to extract fat from anything any product, if you want to get the oil for something else, if you want to extract the oil to do frame analysis in a food product, you can use Soxhlet. You're not after getting all the fat out. If you can get a portion of the fat out and do your analysis on it later, that's fine. But if you want to get accurate results and your matrix is complex, you better go with Mojiner. And then pre-drying, for Soxhlet we had to pre-dry the cheeses because they're high in moisture. However, for Mojiner we didn't. Do you remember from discussion in the lab why? Why did we have to dry the cheeses for Soxhlet but not for Mojiner? Sure, I discussed this with you. Anybody remembers?
Did it
Lauren.
have to like splatter?
Huh?
Did it have to do with splatter?
No, would be for ashing. So when you're ashing, yes, you want to pre-dry high moisture food. But in Soxhlet, we said specifically we have to pre-dry for a specific reason. Okay. Do you want me to save you and just say it? Okay. So for Soxhlet, it's static. You don't have a shaking step, right? It just your thimble is just sitting there and the solvent is going through it and there's a soaking step. So if you have high moisture, the water will act as a barrier to the solvent. And you are not shaking to help that solvent reach the fat. So if you have a lot of moisture, there's a lot of barrier and your extraction will not be efficient. In Mojiner, you put your solvent and you have this shaking movement that you did. So even if you have moisture, you are physically aiding that solvent to reach the fat. So that's why for Soxhlet, high moisture food needs to be dried. But for Mojiner, you don't need to do that. Of course, with everything, particle size reduction, you need to have at least 40 mesh number. So smaller particle size than you would for ash, for example, extraction. For ash analysis, I mean. So particle size reduction is a must. Okay. So solvent selection. So definitely you want a solvent that will not solubilize protein and carbohydrate. You want a solvent that will only solubilize fat, and that would be mostly organic solvents. Low boiling point, so that your extraction is efficient, because we had to evaporate the solvent and goes over to distillation and then drops back into your sample. And when you had to dry the Mojiner, it was faster to dry those pans so that you can get results fast. So low boiling point is a good thing. Non-flammable, of course, don't want it to burst out in flames. Non-toxic, non-hygroscopic. Do you know what non-hygroscopic means? What does it mean, Billy?
They won't extract water from your
Yes. So, for example, the diethyl ether is very hygroscopic, so it gets saturated with water. And if it gets saturated with water, it won't be as efficient of a solvent for lipid as another solvent that doesn't saturate with water. And you want it to be inexpensive, because you will be using a lot of it, especially in Soxhlet. You saw that you had to put 350 milliliter per one sample. Is there a solvent with all these characteristics? No, there isn't. So oftentimes we do combination of solvent if we can afford it. So ethyl ether and PET ether are the common solvents used, but obviously there are other solvents. Like in industry, they use hexane to extract fat from soy flour after pressing the oil out. So hexane is a good solvent, chloroform is a good solvent. So you will see different methods using different solvent, but the methods we've used in the lab commonly use ethyl ether and petroleum ether. Even Soxhlet, you can use a combination of both But for the lab, we chose to use petroleum ether because we use high amount and it's cheaper. So ethyl ether is a better solvent for fat or lipids in general because of it can solubilize polar lipids as well. Petroleum ether is very specific and it's more selective to hydrophobic lipids. That's why if you know the composition of your lipid in your sample, you might go, okay, if I use petroleum ether, I'm underestimating because I'm not extracting all of my phospholipids or monosaccharides or trisaccharides. So if, not monosaccharides, monoglycerols and diglycerols. Okay, it has a lower boiling point and it's more flammable than petroleum ether. And it is hygroscopic. So some have better advantages. One has better advantages than the other. And in this case, solution is to mix. Use both, like you did for Moginer. You used both. For Moginer, we were able to use both because you only use small amount. You use much less. I can't remember the volume. What was it? How much you do? 25 milliliter each? Remember? Something like that? And whereas with the Soxhlet, we had to use 350 milliliter of petroleum ether. Okay, here's the Goldfish apparatus that is no longer seen in labs, but I've used it. And when I was teaching in a different institute, there's a story associated with that. I'll get to this, but let me explain how it works. Okay, so it's very similar to Soxhlet. So you need a hot plate, so here's your hot plate. And then you will have usually a beaker that you would dry and weigh prior to adding your solvent or organic solvent. And then you add a certain amount of your organic solvent. It could be a mixture of ethyl ether and petroleum ether because you would need less than, I mean, you probably put 50 milliliter or 100 milliliter in these tubes, beakers. Okay, and then you have a compartment. And then here, there's a hole, it's open. And then you put your thimble, same as the thimble you used in the lab, that is porous, and you have your sample in there. And then here, you can screw it on, and then you have the condenser. So and then you hook everything up together. So again, the beaker will be attached to this unit. So your sample is really soaked in. But what's happening here, your solvent will evaporate. This is hot clay. Solvent will evaporate. Well, the sample should not entirely be soaked, really. It should be a little higher, but anyway, your solvent will evaporate, get to the condenser, and then goes through into the sample and solubilize the fat, and then comes back into the beaker. So you'll see eventually the beaker will contain the fat and the color changes if you have high fat. So sometimes the process is too fast that you go evaporate and condense and comes back and evaporate, condense and comes back without having the time to carry fat. So we call this channeling, and we talked about that when we covered Soxhlet. So you have channeling, that means the solvent goes through and does not carry fat. So oftentimes this procedure takes longer time to get accurate results than with Soxhlet. And if you can see, these hot plates are very close in proximity to where the solvent is going through. So if you don't screw this on very well, what could happen? Solvent can leak out and hit the hot plate. And diethyl ether is what? Flammable. Okay, so I was teaching one time. in a different place where Goldfish was the unit. I was standing by the hood, so luckily it was under the hood. So I was standing by the hood, and the students were behind me. And then one of the things were leaked. And I was turning to explain, and then boom, in my face. Eyebrows, eyelashes, fringe, all burned off. Yeah, I looked weird for luckily my face did not burn. I still maintained my features. So, but it is dangerous, more dangerous than Soxhlet. Okay, Soxhlet you've all seen in the lab, similar principle. The only difference is this compartment where you put the thimble is closed off. So your solvent evaporates, condenses, soaks the sample, and the best part of Soxhlet is what? The most awesome part of the Soxhlet is what? When it siphons all the way down. And then when it reaches a certain height in this tube, little tube, difference in pressure will cause it to suck down the solvent and siphons back into the container. And since we use 350 milliliter of solvent, it's so hard to evaporate and get the direct weight of the fat. So the better way to do it is get the weight before and after extraction, and that's what you did in the lab. You took the weight before and after, and then the difference would be the fat that was extracted. Okay, there is another story about Soxhlet. You know, I was scarred from the Goldfish, and then I never used Soxhlet before coming here. So I thought, it looks safe. So that was before Cindy was helping me in the lab. So, okay, so I was in charge, so I didn't put it under the hood. And one of my TAs turned the hot plate all to the max, high. And then the solvent was evaporating at so high of a speed, and it was coming from the other direction, onto the hot plate. So I told the students, don't panic, get out. But they were not panicking because they didn't know. I was the one panicking. So send them out and pulled the hot plate from underneath, and nothing happened this time. So it didn't. And then from there on, the Soxhlet is under the hood. And we maintain low pressure, low temperature of the hot plate. So, yeah, fun times. Okay, on that same sheet of paper, yes.
For the Soxhlet, why was it
Oh, you can-
semi-continuous again?
What?
Why is it semi-continuous?
Yeah, for the Soxhlet, why was it semi-continuous? Because what happens is a soaking step.
Right.
Yeah, so they stay for I don't know, a few minutes, and then everything cycles back and the cycle continues. Okay, all right, on a new piece of paper. Let's do some calculations. Okay, for an additional +2. So different piece of paper.
Thank you.
My binders are the best.
I know, I still can't find one that yeah.
So both Goldfish and Soxhlet method are gravimetric, meaning you take the weight and you convert that to percentage based on the weight of the sample. So you can either do that by getting the amount of fat, the weight of fat directly if you have pre-weighed the flask, if we didn't pre-weigh the flask, which we didn't for soft Lect, we took the weight difference before and after fat extraction, and that gave us the weight of fat. If the fat on dry basis is 15%, what would it be on wet basis? Similar to what you did for the ash. If you remember how you would do that. You have a value. Does anybody have a value? Ted?
0.12 or 12%.
It is, yeah, did you all get 12%? Or on your way of getting 12%?
Yeah.
All right, so you have 15%. 15% is 15 grams per 100 grams dry sample, dry matter, right? That's what it means. The 15 grams fat in 100 grams dry matter. If the sample is wet and you have 20% moisture, what's the dry matter in your sample that has moisture? 80. So you have 80 grams. So we're solving for X. So you have 80 grams dry matter in wet sample, in your wet sample. What would then the fat represent? Okay, so it's like 15 times 100 minus 20 is your 80 over 100. You get your X, grams in 100 grams of wet sample. If you do the math, that would be 12%. You get that? Okay. So 15% dry basis, that means 15 grams and 100 grams of dry matter. In your wet sample, you have 20% moisture, so you only have 80 grams of dry matter. What would the fat represent in terms of percentage? That would be this equation here. And remember, always, wet basis is smaller than your dry basis. Okay, then you will know you did the equation correctly. Okay, Mojiner, you've done that in the lab. It's also gravimetric, that means you take the weight of the fat. So you have series of sample preparation, use the unique Mojiner flask, you weigh in your sample, and then you add, depending on the composition of the sample. So if it's high in carbohydrate, or high in carbohydrate and protein, and fat is low, you should use HCl to digest the protein, and HCl to digest the carbohydrate, as well as the protein to release the fat for the solvent. In case of samples that are high in protein and fat and really low in carbohydrates, such as cheeses, you can solubilize the protein that is a curd structure, because cheese are the curd, formed from the curd. So you would solubilize the protein with ammonium hydroxide. And that will release any fat entrapped in the curd structure. And then in both cases, you add ethanol, and what's the purpose of ethanol? Remember from that? We add ethanol to prevent clumping and gelling. Clumping of the carbohydrate and gelling of the protein. Because if they clump and gel once you add the ethyl ether, then you will have the fat entrapped in the matrix. You end up underestimating. So you add the alcohol, then you start extracting with ethyl ether. Petroleum ether is what you use, the combination of both. So we did not have to pre-dry. Like I said, there's a shaking step that you aid the solvent to reach the fat and solubilize it, so that moisture remover is not important. And then after that, what you did is you poured your upper phase, which is the solvent and the fat, into a pre-weighed pan. You dried the solvent out, you weighed the pan, you got the fat content. So that's what you did, and it's a discontinuous, it's a batch process in other words. Other words, you do not evaporate and bring back the solvent. You just use a certain amount of solvent and do that twice. You extract twice, and that's what you did in the lab. We didn't do this in the lab, but it's also a very common and efficient way of extracting fat. And this is using carbon dioxide, but you elevate the pressure and temperature above its ambient, and it can become a liquid form. So you will have the CO2, it goes into a cell compartment where you can pressurize and elevate the temperature, then the CO2 becomes liquid. And you have your sample in there, and there's an oven to increase the temperature. And then the solvent gets redirected into a collecting vial. And here you will have the fat and the solvent, but as soon as the solvent leaves the compartment where the pressure is regulated, it will go back to ambient pressure and temperature. CO2 becomes gas, and that's easy. Then you end up only with the fat. And often it's combined with GC analysis, but for fat specifically, you cannot do GC before you derivatize the fat, obviously. The other form of extraction of fat is elevated pressure and temperature, so that's accelerated solvent extraction. So the solvent, whatever it is, ethyl ether or petroleum ether, again goes into a chamber where you have an oven and also pressurized. So under pressure, it will boil at higher temperature, so you increase the efficiency of the extraction because it won't boil off too fast. So you increase the boiling point, and then you can run it under static or dynamic mode. Static meaning you let it soak, and then you direct the solvent. Dynamic, you open this valve here, and then you will have continuous flow of solvent. You open, close, soak it a little bit, and then open it, and then you will have faster and more efficient, but you use a lot of solvent that way. So you can choose time or money. Last type of wet extraction, it is non-solvent wet extraction. So here you do not use organic solvent. This is very common method for dairy products. So Babcock is an official method of analysis for milk, cream, and cheese. So this is how the bottom look for milk. This is for cream, it's a little wider. And for cheese, you have a stopper because you cannot put the cheese from top. You want to put it directly in that compartment. So this is how you differentiate them. So in this case, there's no solvent. You put in specific volume of milk. I believe it's 17.9 milliliter or something. You have to put specific amount of milk. And then you add specific amount of concentrated sulfuric acid, equivalent amount to how much milk you added. Heat will be generated right away because it was an exothermic reaction. The H2SO4 will start digesting the protein and generates, obviously, heat, and the fat is released. You need a specific amount of volume because you want the fat to be pushed into the graduated cylinder. So the fat will be pushed and it will be liquid form because it is hot. And then you take the measurement. It's volumetric. So you take the volume of the fat. Yes, there is a centrifugation step to help with the releasing of the fat into the upper compartment. And this method, water is not an issue because it is non-solvent base. Okay. Gerber method is very similar. to vacuum, except the tubes are smaller and narrower. So you put less sample and less amount of acid. That's why the reaction is faster and you get faster results. And one additional thing that is different is the addition of ethyl alcohol that prevents charring of sugar if you have sugar content or lactose in milk, basically. Let's continue with that sheet of paper and solve this. So remember, this is a volumetric method, both of them. So we're measuring volume. So we'll say if we're measuring the fat in milk, the density of the fat is 0.9 and the milk density is 1.032. So on volume basis, the percent fat, milliliter per 100 milliliters, 3.5. What would it be on wet weight basis? So on volume basis, it's 3.5. What would it be on weight basis? What do you need to do first? Why is it making this? Okay, what do you need to do first?
Convert to grams.
Yeah, first thing you want to do is convert 3.5 milliliters of fat to grams and convert 100 milliliters, because it's a percentage in 100 milliliters of milk, to grams of milk. Right? So how do we convert milliliters to grams? Huh? Yeah, say that again. Yeah, so volume times the density, you'll get the mass. Because density is mass per volume, right? I didn't put units there, just intentionally. So density is grams per milliliter, right? So you multiply, for fat, 3.5, you multiply by 0.9, and 100 milliliter of milk. You multiply by the density of milk. You get the grams of each. And then what?
Divide by the density.
We're done with the density. We got the grams of milk and we got the grams of fat. Yes, Monica.
If you sum the masses together and then you take the mass of the fat over the total mass.
Yeah, so you don't sum anything. You just take the mass of the fat by the mass of the milk. You multiply by 100, you get the percentage on weight basis. So first we got, okay, don't do like I did, put the units. Okay, so this is grams per milliliter. This is milliliter, sorry, grams per milliliter, you end up with grams. Same here. Then now, this per this times 100 will give you the percentage in grams per 100 grams on weight basis. Good? All right, last bit is the instrumental methods. So, IR, definitely you can use it to measure absorption of radiation in the IR region by fat. It is an online measurement. You can use NIR and mid-IR. Mid-IR is mostly used for milk, specifically NIR for anything else. Of course, remember, it requires calibration. If it's calibrated, you'll get you can trust the results. And it's always calibrated against standard methods, against your Stocksley or Muginer. So if you go to any analytical labs that have IR, they already have a room for the analytical methods. They have the Muginer, they have the Kelda, they have the moisture oven and the furnace to standardize their IR, to calibrate their IR. Fosler method, it's not as commonly used as the other methods. It was even removed from the textbook, the new edition of the. But just FYI, you extract the fat, so you will have your solvent extract from a sample. You measure specific gravity, and then this is the solvent. Perchloroethylene is the solvent. And then you measure the specific gravity, and there is a chart that you can convert specific gravity to amount of fat. So it's very simple if you have the instrument that measures specific gravity. NMR, it is, while the principle is complex, is very simple to use to analyze the fat content. And it's also an AOEC method. So if you have NMR in the facility, it's very easy, and it does not destruct your sample. So you can reuse the sample. It's not a destructive method. That is it. I finished 30 seconds early. So enjoy. I won't see you on Monday, but there is a class for Chelsea. We'll be giving you protein.
I think they are similar, but maybe the equation would be